We are now going to start chapter 5, where we will be talking on inner product spaces and linear operators on inner product spaces. Inner product space is a vector space with an added structure, which is called the inner product or the dot product. And we will see that this will enable us to define the notion of norm on the vector space. First, we define inner product spaces, then we investigate certain basic properties, and finally, we will try to understand the linear operators on the inner product spaces, and we will see that it has a very rich structure. We assume that the field F is either the field of real numbers or complex numbers, and V is a vector space over F. Let us first define what is called an inner product on a vector space V. This is a map from V cross V to the field F, and you can see the map is defined by this symbol, where there are two spots to take care of two entries from the vector space V, and it's an F valued map which should satisfy the following list of properties. So, for every x, y, z in V and scalar C, the first property says that inner product x plus y comma z is inner product x comma z plus inner product y comma z. The second one says that inner product Cx comma z is C times inner product x comma z. The third property says that the complex conjugate of the inner product x comma z is equal to the inner product z comma x. And finally, the inner product of x with itself is positive if x is not the 0 vector. A few remarks. If f is the field of real numbers R, then obviously the complex conjugate of inner product x z is the inner product x z itself, and that is equal to the inner product z comma x. The second one says that if we have an inner product on V, then if we multiply it by any positive real number R, then R dot inner product is another inner product on the vector space V. And the third comment is that for a fixed z in V, the function phi given by inner product blank comma z, and this is a function from V to F defined as phi of x equal to inner product x comma z, is a linear map over the field F. So, if f is the field of real numbers, then it is also linear with respect to the other variable. In other words, if f is the field of real numbers, then this function inner product from V cross V to F is a bilinear function over the field F. So, what is bilinearity? Bilinearity means separately linear in each variable. Some examples. Let us take x an n tuple x1 x2 xn and y another n tuple y1 y2 yn in Fn, and define the inner product of x and y to be x1 y1 bar plus x2 y2 bar and so on plus xn yn bar. This is what we call the usual inner product or the dot product of vectors in Rn or Cn. And the bar obviously defines the complex conjugate. Another example, let V be the vector space of all real valued continuous functions on the closed and bounded interval 0, 1. Given f and g continuous functions on 0, 1, let us define the inner product of f and g to be integration 0 to 1 ft gt dt. This makes sense because f and g are continuous functions, therefore, they are integrable. The product is also continuous, therefore, this is integrable. And then it is very easy to verify that this definition indeed satisfies all the properties of an inner product. The third example says that if V is C0 to pi and then there is a suffix, the set of complex numbers, which denotes the vector space of all complex valued continuous functions on the closed and bounded interval 0, 2 pi. Here again we can define an inner product. Given continuous functions f and g, complex valued, defined on 0 to pi, we define the inner product of f and g to be 1 over 2 pi integration 0 to 2 pi ft gt bar dt. That scaling 1 over 2 pi is necessary for this to be an inner product. Once again, it is not very difficult to verify that it defines an inner product on this vector space of all complex valued continuous functions on 0 to pi. Let A be an n cross n matrix with entries from the field F. Remember that in our discussion the field F is either the field of real numbers or the field of complex numbers and not an abstract field. The adjoint of the matrix A is defined to be the matrix A star given by Aij bar transpose. This is nothing but the conjugate transpose of A. That means we take each and every entry of A, take their complex conjugate, form the matrix and finally take the transpose of that matrix. That is how we define the adjoint of A denoted by A star. For example, if A is this 2 cross 2 matrix with entries I and 0 in the first row and 1 plus I and 1 in the second row, then the adjoint of A star is equal to minus I, 1 minus I in the first row and 0, 1 in the second row. We will see that this notion of adjoint will play a very important role when we talk about linear operators on inner product spaces. Let us look at this example. Let V denote the set of all n cross n matrices over the field F. We know that it is a finite dimensional vector space over the field F. We can define an inner product structure on this vector space given by the inner product of A comma B is equal to trace of B star A. A and B are n cross n matrices with entries from the field F and B star is the adjoint of B. Then we take B star A and take the trace. which is definitely an element in F. Once again, verification is not so difficult, but the following identity is very important when we try to understand the inner product properly. Inner product AA by this definition would be trace of A star A, which is by definition this double summation over I and k, A star A II, that is the sum of the principal diagonal entries of the matrix A star A, and then it is summation I equal to 1 to n, summation k is equal to 1 to n, A star ik aki by definition, but A star ik is aik bar, therefore it is double summation aik bar aki, and that is double summation mod of aki square. Therefore, if inner product A with itself has to be 0, it means that all the entries have to be 0. That means A has to be the 0 matrix. We finally define what is called an inner product space. The pair V comma inner product is called an inner product space over the field F if the inner product function satisfies all the properties of inner product on a vector space V. We often hide that inner product symbol and call V an inner product space to mean that there is an inner product defined on V. V is called a real inner product space if the base field F is the field of real numbers, and a complex inner product space if the base field F is the field of complex numbers. And it is indeed easy to verify that the examples that we have discussed are all examples of inner product spaces. Let us list down some basic properties of the inner product. Let V be an inner product space over the field F. Then the following statements are true for every x, y, z in V and scalar C. Inner product x comma y plus z is inner product x comma y plus inner product x comma z, which says that this inner product function for a fixed x is additive in the second variable. Inner product x comma cy is equal to c bar inner product x comma y, where c bar denotes the complex conjugate of the scalar c. What is important here is that if the base field F is not the field of real numbers, then we cannot say that the inner product is homogeneous in the second variable for a fixed x, because it is not C that comes out, it is C bar that comes out of the inner product. The third part of the statement says that the inner product x comma the 0 vector is equal to the inner product of the 0 vector comma x, and that is 0. Inner product x comma x is 0 if and only if x is the 0 vector, and finally if inner product x comma y is equal to inner product x comma z for all x in V, then y is equal to z. All these can be verified easily if we use the definition of an inner product. Let us now define norm of a vector in an inner product space. Let V be an inner product space over a field F. Now, for every vector x in V, we define the norm of x to be the positive square root of inner product x comma x. Well, it makes sense because we know that inner product of x with itself is non-negative, and therefore, we can indeed define norm x is equal to the square root of inner product x comma x. Let us see some concrete cases. If V is the vector space Rn and x is an n tuple x1, x2, xn in Rn, then norm of x by definition, which is square root of inner product x comma x, that is given by mod x1 square plus mod x2 square and so on, mod xn square whole raised to half. This is because of the definition of the usual inner product on Rn. And we call norm of x the usual length of the vector x or the Euclidean distance of the vector x from the origin 0, 0, 0, etc. Now, the following proposition follows from the definition of norm, which says that for every vector x in V and scalar c in F, norm of c dot x is equal to mod of c times norm of x, and the second part says that norm of x is 0 if and only if x is the 0 vector. We have learned the definition of an inner product on a vector space V over R or C. We have also defined the notion of norm of a vector through an inner product, and you have seen that norm on an inner product space actually defines the notion of distance of a vector from the origin. We will see it more explicitly. Now, we will first prove two very important inequalities involving inner product and norm, and finally, we will define a metric using the norm on an inner product space. These inequalities are known as the Cauchy-Schwarz inequality and the triangle inequality, and both have extremely important geometric consequences. Let V be an inner product space over the field F. The following statements are true for every x, y in V. The first one is what is known as the Cauchy-Schwarz inequality, which says that modulus of the inner product x comma y is less than or equal to norm of x multiplied by norm of y. The second statement says that norm of x plus y is less than or equal to norm of x plus norm of y, which is called the triangle inequality. And the third one says that modulus of norm of x minus norm of y is less than or equal to norm of x minus y for all x, y in V. Let us first prove the Cauchy-Schwarz inequality. We first note that if the vector y is the 0 vector, then the statement is obviously true. Why? Because the inner product of x comma 0 is 0 and y being the 0 vector, norm of y is 0, and therefore, we in fact have an equality there. Let us therefore assume that y is not the 0 vector. Therefore, inner product y y is not 0. And we look at the norm of this vector x minus inner product x y by inner product y y times the vector y. We in fact look at the norm square, which is therefore non-negative, but we know that norm square is nothing but the inner product of the vector with itself. Therefore, it is equal to inner product x minus inner product x y by inner product y y y, comma x minus inner product x y by inner product y y y. And now we use the standard properties of the inner product, and finally what we get is inner product x x minus this inner product x y multiplied by this scalar conjugate of inner product x y by conjugate of inner product y y minus the inner product y x multiplied by the scalar inner product x y by inner product y y, and plus what you see over here, that we have in the numerator inner product x y into inner product x y conjugate, and in the denominator we have inner product y y multiplied by inner product y y, and finally inner product y y. So, if we simplify, then we finally get norm of x square minus modulus of inner product x y square by norm of y square, and that is non-negative, and therefore, a simple rearrangement gives our result. Proof of the second part, that is triangle inequality. Norm of x plus y square is nothing but inner product x plus y comma x plus y. Again, by the defining properties of the inner product, we get inner product x x plus inner product y x plus inner product x y plus inner product y y, which is the same as norm of x square plus norm of y square, and inner product y x plus inner product x y gives rise to 2 times real part of inner product x y. That is because we know that inner product y x is the complex conjugate of the inner product x y, and therefore, when we add a complex number with its conjugate, what we get is twice the real part. This is less than or equal to norm of x square plus twice modulus of the inner product x y plus norm of y square, and now we can apply the Cauchy-Schwarz inequality to get less than or equal to norm of x square plus twice norm of x times norm of y plus norm of y square, and you can see that this is a perfect square, and that is equal to norm of x plus norm of y whole square. This proves our result. Now, we prove part 3, which is a straightforward application of the triangle inequality. So, let us start with norm of x, rewrite it like this, norm of x minus y plus y, apply triangle inequality to get less than or equal to norm of x minus y plus norm of y, and therefore what we get is norm of x minus norm of y is less than or equal to norm of x minus y. But you see, this inequality is true for every choice of x and y in V. Therefore, we can also interchange x and y in this inequality, and that gives us norm of y minus norm of x is less than or equal to norm of y minus x. But norm of x minus y is the same as norm of y minus x, and what you see on the left hand side, there is only a difference in sign, and therefore we get our result that modulus of norm of x minus norm of y is less than or equal to norm of x minus y. A remark: it can be proved easily that modulus of inner product x y is norm of x times norm of y if and only if y is equal to lambda x for some lambda in the field f. In other words, the Cauchy-Schwarz inequality is in fact a equality if and only if y is a scalar times the vector x. This is not difficult to prove, and in case of the vector space R2, the Cauchy-Schwarz inequality is rather easy to prove, because modulus of the standard inner product of the vectors x and y is given by modulus of norm of x times norm of y times cosine theta, where theta is the angle between x and y, and therefore this quantity on the right hand side is less than or equal to norm of x times norm of y, because modulus of cos theta is less than or equal to 1. Cauchy-Schwarz inequality can be proved by other techniques too. What we have discussed here is a geometric technique. We can also use analytic techniques to prove the Cauchy-Schwarz. Let us now define what is called a metric on a non-empty set X. It is a function d from x cross x to the set of real numbers R, such that d of x comma y is greater than or equal to 0 for every x y in X. D of x y is equal to 0 if and only if x is equal to y. D of x y is equal to d of y x for every x and y in X. And finally, which is also called the triangle inequality, says that d of x z is less than or equal to d of x y plus d of y z for all x y z in X. We first note that a metric is defined on a non-empty set, and the non-empty set X need not have any algebraic structure on itself. On the other hand, we have learnt in basic topology that a metric on a set gives rise to a topology on the set, and that is how we define a metric space. What is interesting is that if we have an inner product space over the field of real numbers, then there is a natural metric coming from the norm and defined as d of x y is equal to norm of x minus y for x y in V. Properties 1, 2 and 3 are easy to verify. Let us check the triangle inequality for D. So, given x, y, z in V, let us first write dxz, which is nothing but norm of x minus z. We rewrite it as norm of x minus y plus y minus z by introducing the vector y. And we know that triangle inequality is true for norm. Therefore, it is less than or equal to norm of x minus y plus norm of y minus z, but that is d of x y plus d of y z. We have learnt definitions of inner products and norms, and we have proved two very important inequalities, namely the Cauchy-Schwarz inequality and the triangle inequality on an inner product space. We have also seen that the notion of norm naturally gives rise to a metric on an inner product space, which in turn gives rise to a topological structure. So, an inner product space is not only rich algebraically, but also topologically.